So we were discussing integrable and non-integrable Hamiltonians yesterday, and also the question about action angle variables and gravitational and tori in phase space. And so one of the tools we were looking at was the surface of section, which is shown here again. That's a mapping from a plane in the phase space to itself after the respective orbital periods of the stars. And I've shown you surface of section here on the left and the corresponding projected plot for a torus. And you can see that the surface of section in this two-dimensional Hamiltonian is sort of a cross-section through all the tori in the system. So imagine this is my plane Q2 equals 0. Then it'll map stars as they move around the torus, and they come next time, not to this, but the other side here again with the same, intersecting the same plane. They now will intersect this plane at a somewhat different point with a different velocity, and that'll correspond to a different point on this invariant curve here. So the torus is a geometrical structure, and in these two-dimensional Hamiltonian systems, the surface of section is one way of mapping out one of the cuts through the torus. So you can also see that different tori that correspond to different orbits will have different shapes and cross sections here. So you might imagine that this torus here contains a torus of smaller excursion, and in the middle of the structure would be one that is actually a very small compressed torus that contains the periodic orbit. So then we were looking at the coordinate system of angle action variables, and essentially the action variables measure you something like the cross-section of the torus, the independent cross-section of the torus. So this is one of them, and then there's a second cross-section that would be a cut through the torus this way, except that it isn't drawn properly because I would need a four-dimensional space to draw it the same way as I've drawn this way. And so we can only see it in one direction properly, but the other direction, the other cross section, you can imagine something like this would give you the alternative action. So it's also true, you have to remember that any function of the actions is also an integral, and so given those cross-section actions, you can then, for example, map to other linear combinations of actions that would also be conserved. So that's the action variables. They're particular integrals of motion. For a system that admits integrals, then the actions would be functions of the integrals, and they would have this property of measuring the areas of these cross sections. The angle variables are the part of the canonical coordinate system that describes the motion on the torus. And they, as you remember from yesterday, evolve linearly with time. Each torus is characterized by the actions, but you could also say it's characterized by the frequencies with which the orbits move on this torus. And then the angle variables evolve like omega times t. Now, this surface of section only has invariant curves, as you see, these one-dimensional curves that signify you that besides the condition that the energy is constant, the cross-section is defined, there's a second integral of motion in this two dimensions. So this could be a surface of section for an integrable system. It's actually not. It's for galaxy potential, and so if you look closely enough, there are some regions in here where you would not have an invariant curve like this anymore. And that's where the power of action really comes in, because as I told you yesterday, these little tiny regions of irregularity, even a system like this, are everywhere. So you cannot define a function of x and p, or q and p, that's constant along orbits everywhere in this phase space. There's no global second integral. But still, for all of the invariant curves here, you can still determine the action variables by suitable methods. And so, because they're local to the torus. And so even though there's no global second integral, you can still make approximate mapping to an action angle space and in this way describe your invariant curves. So is this somehow become clear what the meaning of action angle variables is and also the advantages? If not, please ask. Okay, so now here is a surface of section where you can see it now more explicitly that some of these, what used to be invariant curves around these two families here, have broken up in a set of resonant islands. Now, these resonant islands now become the centers of some stable motion, but there's also the part here that's not drawn, which is whenever you have a breakup in the resonance, you have these unstable fixed points in the middle here between all of these islands. That's where then the chaos starts developing. This is the source of the unstable behavior. And I had this somewhere. Okay, sorry, which way we're going? Here. See, these are the points that in a pendulum would correspond to these points here. That's when the pendulum just goes up to the top. And then, since the one-dimensional pendulum is integrable, this is here a well-defined point with curves arbitrarily close to it. But the moment this is no longer integrable, then if you put a perturbation on the pendulum, then very close to this unstable point, the orbit sort of can't decide anymore which way it should go and which orbit family it should belong to. And so this is the source of the small chaotic regions that develop around these unstable orbits. So the Poincare-Birkhoff theorem told you that this implies, because near these resonant tori the orbits break up first under any perturbation, and this implies, because there are resonances everywhere in phase space, arbitrarily close to any point there's a resonance, that almost everywhere you have some very tiny islands and small chaotic regions in the perturbed system. And therefore you cannot have a global analytic function that's conserved along orbits anymore.
So
Please.
if you are close to these chaotic points,
Mm-hmm.
does that mean that you can expend only a very small amount of energy to put the particle in any kind of orbit?
So this is for orbits on an energy surface, because energy is still conserved. But in some sense, I think you're right. A small perturbation around these points would be able to move the orbit from one of those librating orbits to one of those oscillating orbits. And part of the chaotic behavior is that orbits close to this in this region would actually do this by themselves. So they would for a little while behave almost like an oscillating orbit, but then go over into a librating orbit and back. Yeah. So it turns out, and you could see this from this plot here. This is a simple model potential. That I think it's a logarithmic potential, if I remember. This was a long time ago. And so this is not an integral potential, but it looks not so bad. It has a lot of invariant curves here, orbits that look regular. And so this is something that perhaps one could not a priori have expected, but it's true that many galaxy-like simple potentials, at least, smooth simple potential, turn out to be near integrable in this sense that a large fraction of phase space is still described by regular orbits on invariant tori. Now, it's also true, one has to say in brackets, that the real potentials may be more complicated than the simple potentials we've been investigating to model galaxies, simply because, as I showed you in the first day, in our hierarchical universe, there's always something going on. There's subhalo secreting, there's other perturbations like spiral arms of the disk and so on that sort of change the potential. But still, this will keep a large fraction of this phase space still regular, even though perhaps the fraction is not as large as in some of the simple potentials. So in these near integral potentials, we could see that you can define action angle variables on the torus to the left, and sometimes you could even try and describe by some kind of average action angle coordinate system a small chaotic region, even though it's not strictly true. So one thing I like to say is at the end is when you read the literature, astronomers often speak of so-called three integral models. And so in the strict sense, this isn't correct because there is no third integral in these potentials. What they mean and is this sense here, that most of the phase space is described by regular orbits, and then they explore those regular orbits by using various methods. For example, a Schwarzschild method of integrating orbits and then putting together your distribution function from that. This is something we come to later. So now I want to go to some more simple examples again. So here is an axisymmetric potential, phi, and when it's axisymmetric, then the angular momentum is conserved. And so, as you may remember, you can define an effective potential. This effective potential has the angular momentum term here added in this way. And then, because this is conserved, essentially the motion reduces to a two-dimensional motion. So you can describe by two equations of motion in the so-called meridional plane, R and Z, which are just simply given by these very simple potential derivatives in terms of the effective potential. And then the third dimension is described by this simple equation where the phi dot variable, the angle here around the symmetry axis, evolves according to L over R. And so this plane, phi of t, once you solve R for this equation, you can put it in here, and then you know what phi dot is. And so the meridional plane then rotates with the star in this way. But you don't really need to consider it so much because it's defined by the angular momentum. So the other issue about these effective potentials is that this L squared term creates a centrifugal barrier for almost all orbits, except the ones that have really zero angular momentum. And so this means that orbits are confined between minimum and maximum radii. And so this is how they typically look. This is some plots from Binney and Tremaine in this particular logarithmic potential that is often or sometimes used as a simple description of dark matter halo dominated galaxy potentials. You can see here this is radius, this is Z, and so the orbit has a maximum extension in R and also in Z, whereas the Z1 depends on R. This is an orbit that is more confined to the plane, whereas this one is one that explores a larger fraction of the volume. And those two in the surface of section have those shapes here. So there's a invariant curve here describing this orbit that's and here, and then there's a larger curve describing this other orbit there. So these are, to the accuracy of the calculations here, are regular orbits. They would be, for those orbits you could construct an action angle variable. So in axisymmetric potentials, there's a variety of orbits, and I wanted to show you this plot here, how you might label them. So you can see that, for example, you could label them with action variables, but you could also label them with turning points. Turning points are, in some sense, integrals in quotes. Also, the turning point here is the limiting radial points r min and r max on the equatorial plane, maybe, and then these angles here you could use to describe the turning point. And that goes back to the Steckel potential that we looked at yesterday, because these orbits have some characteristic features in common with the orbits we saw yesterday in the Steckel potential, the confocal coordinates being the limits. And so one can construct shape invariants. There are some measures of how far the orbit extends in various directions here, and then you can sort of plot the orbit space, and for example, these 6 orbits here from A to F, they would be found in this space here on these various points. And this space is delimited by the set of orbits here, which are completely confined to the equatorial plane, so their vertical excursion is 0. There's another set that is that has a radial thickness 0. You could see that by bringing the inner and the outer limiting radii together, you end up with a shell orbit. And then there's a third limit, which is the orbits of 0 angular momentum, which are those orbits that are in the meridional plane without any angular motion. And these sort of more general orbits would live more or less close to any one of these 3 boundaries. So now let's go to triaxial potential. And again, there is one class of integrable potentials which can be written in these confocal ellipsoidal coordinates, defined here as ellipsoids lambda. That's these here. Then there's a hyperboloid of the first kind, defined these coordinate mu here. You can imagine these coordinate surfaces, and then there's one of the second kind for the third coordinate. And again, like in the 2-dimensional case, orbits would be defined in these potentials as living between coordinate surfaces. It's a separable potential, and you can see this is an illustration of how the orbit families that can live in these Steckel potentials might look like. Here you have a loop orbit around the short axis, and that is in some sense a generalization of the orbits we saw earlier. This is in the meridional plane, so if you wanted to do the same 3-dimensional representation, you would sort of have it go around the symmetry axis, and so you can see that that's sort of almost quite close to this one here, except this so-called short axis tube orbit is no longer axisymmetric. It's squashed in one of the directions along the axis in the plane. And then there's now a new family that oscillates around the long axis of the potential. So that doesn't of course happen axisymmetric potential. That's new, and that new family has an inner and an outer variety which depends on the energy of the orbit, and that's to do with the coordinate system. So perhaps the main message is that for a triaxial stacker potential compared to an axisymmetric one, apart from these Z-loop orbits, you also have the X-loop orbits that go along the long axis, and then you have this final family, which is called the box orbits, which essentially go near the center and then sort of open up on both sides once they've gone through, and they can be thought of as generalizations of these orbits, where here that you have a boundary because of the angular momentum, but in the triaxial case, the angular momentum is no longer conserved. And so there is a family of orbits that goes right to the center, comes on the other side, has this sort of characteristic butterfly shape. And that's not only true in this direction, but also in that direction. And so in the end, you end up with a three-dimensional shape of this kind. That's generally new in triaxial systems. Now, these separable potentials are interesting in the sense that they set certain properties of the phase space that you also find in nearby potentials, but they're not general, and some of the properties also don't survive in general potentials. For example, it is possible that general potentials have some chaotic orbits, yes, but also what is quite often found when you look at galaxies, that the central density rises inwards at some power law, and this tends to, as a steeper the power law, destroy this family of orbits, and I'll show you that in a moment. This is again a two-dimensional system. Now we've compared the original logarithmic potential, where there was a softened core in this potential. We've now removed this core, and so this is a purely logarithmic potential, meaning the density is like 1 over r squared, but the orbits are also flattened. I think there should be a flatten in here. And so now the box orbits that used to be present in the surface of section, this is now plotted slightly differently, these families here, they break up into various resonant families. This is one of the manifestation of this general process. But what's surprising in here is that these resonant families that now replace these two-dimensional box orbits, they have these various low-order resonant forms. At that time, they were called banana and fish and pretzel orbits and of this kind. Here's the periodic orbits that replace the simple orbit along the long axis that sired the box orbits before. And so that happens because the original orbits become unstable, and then new families become stable instead, and then contract the phase space around them. And so that's something that also happens in the three-dimensional case, only that it's more complicated there. Okay, I don't want to go into the details of these orbital structures much more. This was just to illustrate you that in some cases resonant orbits are very important, and they then need to be taken into account in the dynamical structure as well. So let's come to orbits in disks, and the simplest orbits you all must have heard about it is orbits of disk stars that are nearly circular, and that one describes by the so-called epicycle approximation. So again, you write the potential as this effective potential phi plus L squared over 2r squared, and that has a minimum when you have a circular orbit at r equals to what's called the guiding center radius, or Ken was using the word home radius, I think, for this orbit. And so then if you consider a circular orbit in the plane of the disk, and then you Taylor expand your effective potential around this guiding center, then it'll be quadratic, because the potential has this characteristic form. And so at the bottom you have a quadratic expansion. And then you can write it as the value on the circular orbit plus some quadratic term in x, which is the difference in radius to the guiding center radius, and the quadratic term in z, which describes the excursion from the plane of the disk. And then in this approximation, there's two orbital frequencies here. This is a harmonic term, and so the quantity kappa here is the frequency that governs the radial oscillation, so-called epicycle frequency, and this is the vertical frequency nu that governs the frequency, the motions in the vertical direction. And so your solution in this approximation is very simply given by this set of simple equations, where both the radial excursion of the star relative to its circular orbit is a harmonic oscillation with some amplitude A and this frequency kappa, and the vertical amplitude has an independent amplitude, an independent frequency, and finally the azimuthal motion is essentially given by the regular rotation of the circular orbit plus some perturbation around it, which follows the same frequency kappa with some different amplitude given by A, this A, times this frequency ratio. And so what this comes out geometrically is that if your circular orbit goes around the galactic center this way, then your epicycle is now an excursion of the star with frequency kappa that goes around the guiding center on the circular orbit in this retrograde fashion in such a way that the amplitude of the excursion is larger in the azimuthal direction than in the radial direction. And you can also work out, and you find that in the textbooks, that corresponding to this excursion, if you consider an ensemble of stars, is a mean square velocity dispersion of the stars around the guiding center, sigma r squared and sigma phi squared, where actually sigma r squared is the larger one than sigma phi squared. And for a flat rotation curve, it's the same factor 2 omega over kappa, which is going to be square root of 2. So these are epicycles. Now let's say we go to a rotating potential. We know our galaxy has a rotating bar, and so it's interesting to understand orbits in rotating potentials. And again, let's start very simply. Consider now a motion in a coordinate system that's rotating with the bar. Why would you do this? Because if you stay in the inertial coordinate system, then because your bar rotates around the galactic center at some pattern speed omega, then your potential will be time dependent. And so if you go into the rotating potential, you can eliminate that time dependence, which is always advantageous. So that's the reason. And then in this rotating coordinate system, with angular frequency omega, the Hamiltonian would then become this one called Hj, which is the original Hamiltonian, in other words, including the gravitational potential of the mass distribution, minus omega dot L, where omega is the angular momentum vector corresponding to the pattern rotation of the bar, and that you can write as h naught minus 1/2 omega squared times r squared. Now h naught includes the gravitational potential generated by the mass distribution of the bar. And so again, we can write an effective potential, which now is somewhat different. It's given by the original potential determined from the mass distribution using Poisson's equation, if you like, and then minus 1/2 omega squared times r squared. And so this phi f is time independent. And so it means that this hj function is conserved along the orbit. So that's it's the quantity that replaces the energy in a rotating potential, and it's a strict integral of motion in such a uniformly rotating coordinate system. So then you can make a plot of this effective potential phi f, and this has this shape here. So we're looking at elongated potential surfaces. So this is the long axis of the bar, and you can see here there's 5 points indicated. These are the so-called Lagrange points. That's the stationary points of this effective potential. One is in the middle. So if you put a particle in the middle and it's non-singular, then it will stay there. And there's two along the major axis L1 and L2, which are always unstable. They're sort of saddle points. You can see that the potential will rise towards this end, and then it'll have this it's called convex shape in the other direction as you leave the inner regions. And then there's two other Lagrange points which are maxima of this effective potential, and as it happens may be stable or unstable. So that in some cases there can be families of orbits oscillating around these Lagrange points. Now this red circle here is called the co-rotation radius. That's the radius where the angular frequency of the rotating bar is equal to the angular frequency of a particle in the mass distribution. So that's also the reason why on this circle is where the Lagrange points, the stationary points, must lie. No, it's in for small perturbation. Yeah. Okay, so now let's go at and have a look at orbits in these rotating potentials, and it's useful to first consider small perturbations always. So we now take an axisymmetric system potential, and we add a weak potential perturbation which has this form, some radial amplitude phi b times cos m phi, which is supposed to be rotating with this pattern speed omega b. Then you can linearize the equations of motion. The way you do this kind of perturbation theory is you follow an unperturbed orbit, just like in the epicycle case, and you ask about the perturbations around this orbit introduced by the perturbation of the potential. And then if you want to follow the details, you find that in Billian terrain as well. You can boil this down to this equation here for the radial excursion around the original circular orbit, and it has this characteristic term. It's now an oscillator, but it's also perturbed by this rotating multipole from the potential. And then if you remember the fact that by following this perturbation around the original circular orbit, you can write time as the angle along this orbit divided by the relative frequency, and then you can write down the orbit equation for this excursion R1 as a function of phi 0. And so that's given here. You don't need to now understand all of the details, but the interesting thing to note here is that when you look at these terms, first of all, there is a term that's simply oscillating here with phi 0, and then there's a term that's more complicated. Now, suppose we set this C1 equal to 0, then you can see that this term here closes after a number of oscillations m, and so that's a closed orbit perturbation in this plane. And then there are these perturbations of this closed orbits that are given by this first term. So that's the first thing. And the second thing is what to notice is that these equations have so-called resonant denominators. One is at the point where omega equals to the pattern speed of the perturbation. So that's the co-rotation radius again. And the second is where this quantity delta here becomes zero. This is described as Lindblad resonance. So here the epicycle frequency of the original orbit resonates with m times the relative angular frequency in the frame of the bar. Now these resonant denominators mean that your analysis isn't going to be valid anymore, and that's something that just happens because we did this linear perturbation theory, but it is more generally relevant in the following sense. Let's look at the Lindblad resonance and the co-rotation resonance first. So here's a plot of angular frequency versus radius for a typical mass distribution that we might have in a galaxy. And you see this is the curve omega as a function of radius. It's decreasing. Typically, rotation curve in spiral galaxies is about constant, so omega would be roughly like 1 over r. And here is the two corresponding curves for the Lindblad frequency, omega plus kappa half for m equals 2 perturbation now, and omega minus kappa half. These are for m equals 2 these points where these frequencies where delta would go to 0. And now let's look at some rotating perturbation and give it this pattern speed omega p. Then you see this constant frequency would cut those three curves in these points here, here, and here. And these are then the location of the resonances in your mass distribution in your disk. So that would be the co-rotation resonance where omega equals omega p. This is the outer Lindblad resonance where omega p is omega plus kappa half. And this is the inner Lindblad resonances where this is equal to omega minus kappa half. So what's the significance here is that when you look at the orbits in such a potential, then these orbits change the orientation at any of these resonances. So typically in a barred potential, even potentials that are perturbed by more than small amounts, so where linear perturbation wouldn't be valid, you still find typically that inside of the inner Lindblad resonances, you have this family of orbits that's orientated along the short axis of the bar, so-called X2 orbits in the notation of Contopoulos. Then as you cross outwards, you find the main family of orbits elongated along the bar, the so-called X1 orbits. And then as you cross the co-rotation radius, which is somewhere here, then you're going to have again orbits oriented along on the short axis of the bar. And when finally you go past the outer Lindblad resonance, it should be the other way around. So that's these main families. And then you think so? Okay. Anyway, the principle is orbits change shape every time you cross the resonance. Then we have, in addition...
You mean that X1 orbit couldn't exist beyond the resonance?
That's right. I mean, the X1 orbit exists up to the co-rotation radius, but actually not even up to the co-rotation radius, because this is one of the examples where resonances become important, because you can see that as you approach co-rotation, the relative frequency comes to 0. No? So there are very many resonances near co-rotation. And in fact, some of them become stable resonances in these potentials, and they would then, for example, sire orbits like this, which is a 4-1 resonance. And then in addition, there can be orbits around the Lagrange points, which you see here. So these are some non-periodic orbits. Non-periodic orbits follow essentially the periodic orbits, but they have some epicycle oscillation around it. And this you can see here. This is Barr potential. Again, here we have the X2 orbits. This is the X1 orbits. They both rotate in the prograde sense in the pattern of the bar. So that means that, let's suppose the bar rotates this way around, then the star on the orbit in the rotating potential also rotates this way around. That's called prograde. If the star was to go the other way around than the pattern, then that would be called retrograde. There are such orbits, but they're usually not occupied, because it's so difficult for stars to be scattered onto them. And so here's one of the X1 families with an excursion, so non-closed orbit. And you see here, this is a thin orbit in the bar, and this is a sort of thicker orbit in the bar. They can develop these loops at the end, and sometimes I think called ANSE now. And they leave this when for sufficiently small epicycle perturbation, they leave this hole in the center, which is due to the Coriolis force in the equations of motion. So now this is one of the cases where chaotic orbits may play an interesting role in galaxies, is these rotating bar systems. Now in this surface of section here, you can see the main orbital families that we were looking at just now. Here is this is the y-axis coordinate versus the velocity along y. Here is the main X1 family. This is the orbits that go along the long axis of the bar, and then the periodic orbit at this energy, at this value of Jacobian Hamilton HJ, Jacobi integral, would be at this point here. The resonant, the periodic orbits, then orbits that have a perturbation around this resonance sort of follow these invariant curves here. The same is true for the X2 orbits that in this notation are here. And again, you have a closed orbit at this value of Hj and orbits that oscillate around the closed orbit and follow these invariant curves. And then on the left here is the retrograde X4 family, which is there in the phase space, but may not be there in your model very much. Now, once you go to large excursions around the periodic orbits, just as we were saying in general, you start having other structures in the phase space. That's when you, if you like, approach these unstable points, and so then the tori would break up into little resonant islands first. And when there are many, such resonant tori that all break up into islands, then this leads to the development of chaos. There's a concept called resonance overlap due to Chirikov, which describes that. And so if you imagine the influence of one resonance growing in the phase space, at the same time the influence of the neighboring resonance growing in phase space, at some stage the influence region of both the resonances will overlap. And once they do, these orbits will no longer be able to understand which resonance they belong to, and then they start moving freely in the relevant part of the phase space and leading to this chaotic region. And when there are many resonances overlapping, then you get a strongly chaotic region, like in this case here.
So Ortwin, are all those points 1-1?
All points. This one, I suppose so, but I haven't checked actually. But I mean, it wouldn't make sense to plot more than one. Yeah. So there's. you put them.
Yes.
Yeah. Okay. So this is another interesting concept that is also, I think, still not completely understood. Is that to what effect, what degree does one orbit fill this entire chaotic orbit with time? No? I mean, if one of the simple limits on the opposite of regularity is that the orbit is ergodic in this part of phase space, which means that it would basically go to every point it's energetically allowed to, and to every point it can go to, given the limitations from invariant curves. In 2 dimensions, chaotic orbits cannot penetrate into regions of regular motion around invariant curves. And so in the ergodic limit, such a chaotic orbit would fill this region uniformly, and this is not so different from what you see here. But there are cases when certain regions of this chaotic space are separated from others, the so-called cantori, and then even though the region looks chaotic, it may mean that the orbit still can't, or only after a very long time, fill this region completely. In the bottom panel, this is just 2 different chaotic orbits. Yeah. They're different chaotic orbits, and because this one is confined by invariant tori here, it cannot move out, cannot break out into this region here. That's, however, special to 2-dimensional systems where the tori are 2-dimensional, and therefore they foliate the energy surface, which is 3-dimensional. When you go to higher dimensional systems, like in 3-dimensional mass distributions, your tori are 3-dimensional, but the energy surface is 5-dimensional, and so there's an extra dimension, and the orbit can sort of come through that extra dimension, and then it would be possible to go from here to here, even though it looks like it's confined. But that's a bit too much. So-called R0 diffusion. So now we're coming to 3-dimensional bars. This will be relevant for some of the galactic bulge work tomorrow. So here now we have a set of periodic orbit that was first worked out, I believe, by Daniel Pfenninger. He used a rotating Ferras bar. That's some mass distribution we don't need to worry about. Some long bar, relatively thick and in the horizontal direction and thin in the vertical direction. And he was then finding the periodic orbits in this rotating potential. And now, in addition to having the 2 planar coordinate motions, you also have the oscillation in the 3rd dimension. And so here are now orbits that are resonant. For example, this is an orbit that has a ratio of radial to frequency 4:1. So you can see that for every motion once around the center in the angular direction phi, it's going through these 4 loops corresponding to 4 radial oscillations. So that's this 4:1 resonance ratio. And at the same time, it's going up and down in various ways, corresponding to 6 vertical oscillations. So it's a resonant family. It's 4:1 to 6. And in the other panels here, you see other resonant families. This, for example, is called 4:1,4, according to the 4 oscillation radial, 1 around the center and 4 going 1, 2, 3, 4 in Z. And this one is a 2:1 to 4. And so the phase space now breaks up in a number of these families, some of which, if you look at the general orbit, would be the backbone, if you like, of a family of periodic orbits that have the same similar structure, but now have some oscillation in two directions around this periodic orbit, just like epicycles. Okay, let's see. Okay, this is now from a later paper of Pfennigers and Friedli, and here some of the orbits that they found in n-body simulations are plotted, and you can see this is X and Y, and there's some perspective plot of the same orbit here, and there's Z, and so you can see that these orbits can look like this sort of bent bananas, I think they're called, some of them, and then there's the anti orbit of this, which looks a bit like a figure of 8. And here's the projections in the XY plane. They look basically like X1 orbits that we had in the plane. You see the center here, and then here you have these loops, and then you have the rotating. So these are prograde orbits in the equatorial plane. At the same time, they oscillate in the vertical direction. For example, like this, but also sometimes like in this figure 8 shape. Usually one of those is stable, and the other is unstable, but that may change depending on where exactly, at what energy you look. So in these three-dimensional potentials, the orbit structure can get very complicated. Is one of the messages, and we will see that these kinds of orbits play an important role in three-dimensional bars. So now let's leave the subject of orbits and go to Jean's theorem. So this is now going back to the theory. We were saying that the distribution function follows the collisionist-Boltzmann equation. And so if we're looking for a stationary solution to the Boltzmann equation, then the distribution function must depend on other quantities that are time independent, and that's the integrals of motion. So if the galaxy is a steady state, E by t equals 0, then Jean's theorem says that the distribution function depends on the isolating integrals of motion and on the independent integrals of motion. Now, independent, of course, means I can construct always a function of integrals from each I. I can construct a function of I, but these are not independent. No, they don't describe a different torus, if you see what I mean. So you need independent integrals, and then they should be isolating. That means they should confine the motion to a subset of phase space. And if you remember yesterday, all the integrals in involution have that property. And therefore, we also know that in a general potential, there are 3 isolating integrals of motion, if there are integrals of motion. And so then the distribution function would depend on I1 to I3. Now, examples, let's look at the classical systems. In a spherical potential, we have the energy as one integral of motion, and the 3 components of the angular momentum as integrals of motion. So that's actually 4. And so the spherical potential is special, and the reason is, if you like, all orbits are resonant in the spherical potential, and this implies that they're all confined to planes, and different planes are in principle distinguishable. So the distribution function could be, in principle, a function of 4 integrals of motion. However, then the system wouldn't be spherically symmetric. And so the spherically symmetric equilibrium distribution in a spherical potential depends on energy and the square of the angular momentum vector. Now, in axisymmetric systems, the classical integrals are E and Lz, and then you can construct distribution functions depending on those 2. But as we'll see, these are not the most general ones, because the most general distribution function should depend on 3 integrals of motion, provided they exist. And in the general potentials, we only have the energy, And well, for example, in a triaxial potential, we could write down a function of energy only, but it's not hard to convince yourself that that's not a valid solution to any equilibrium problem. So there, certainly we need other quantities, the actions, in order to make a valid equilibrium distribution function. So that's the non-classical integrals. There's the Stecker potentials I showed you, where we can write them down explicitly. And then there's all the other potentials where we can't write them down explicitly, but we sort of know that at least for a large fraction of the phase space, you have action variables defined on the tori that survive. And so then the distribution function would now depend on those quantities. So I wanted to illustrate in one sense what this means and why it's useful. So Jean's theorem is a global theorem. It tells you that the overall distribution function of the system depends on those integrals of motion. And that's good because if we, for example, put ourselves at the position of the sun here, we can observe stars in various directions. They're even with the Gaia data, we could observe the positions and the velocities. We may not be able to observe the stars on different parts of the orbit. But we know by Jean's theorem that the phase space density in different parts of the same orbit must be exactly the same as the phase space density on the same orbit near the sun. And therefore, by considering orbits or tori, we've reduced the dimensionality of our phase space, if you like, and therefore we have a lot more information about the system than we might a priori think. So what it implies is that different parts of the system are dynamically coupled through the orbits, and by using a global model, you can exploit that. So now we said there aren't isolating integrals for all potentials, certainly not analytic ones. And so you can generalize Jean's theorem in the following sense. You can say if your potential doesn't admit analytic isolating integrals, but it's still near integrable, you can say my distribution function can depend on the invariant tori, or it could be depend on the action that describe those tori, or it could also be written as a function of the orbits that move on those tori. And if you think of your phase space geometrically, all of these three things are the same, which is the power of looking at it geometrically. You don't need to describe it by an analytic function anymore. You need to compose your system only of the invariant geometric structures in phase space, those tori or orbits, if you like, or whatever else you have to describe them. Now, this doesn't work. This works in all of the near integral potentials, but it doesn't work in systems which have significant chaotic regions. And then it's sometimes possible to even take that into account by this concept of invariant ensembles. So let's suppose we're in one of these strongly chaotic systems like the region, the Barred galaxy, and we're looking at the co-rotation region, and let's suppose this is a strongly chaotic region in which the orbit actually fills the chaotic phase space quickly. Then we can, in principle, by following individual orbits, look at the distribution of density that this orbit follows, even in the chaotic region. And this we can consider as a building block of our distribution function, just like a torus. And again, it's this concept of a geometric structure, this region in phase space explored by the orbit. Now, of course, when it gets more complicated, when you have regions that are not filled quickly by the chaotic orbit, then this is not entirely straightforward anymore. And then such systems will actually evolve with time, simply because the orbits evolve with time, over a long time scale. Okay, I think I'm out of time, so I should stop. So this is a generalized Jean's theorem. Now we have the tool to actually construct dynamical models of galaxies, which are basically distribution functions depending on those integrals or actions or orbits. And I will do that tomorrow. And then I want tomorrow to start discussing the galactic bulge.
We move to yes.
Just going back to what you were saying about having Rmax and Rmin and Zmax as basically integral motion.
Mm-hmm.
I mean, what do you really gain by going through the whole torus procedure that you haven't already got from those three alone?
It depends. If you're only interested in making an equilibrium model, you can in principle do it in this way. It is sometimes a little tricky to do because for the simple orbit families, they're easy to determine those turning points. But for the more complicated ones, it's not so easy. So that's one issue. And the second is if you think about adiabatic invariance in slow evolution, then of